Perfect. So let's start off with a optimization problem, and allow me to share my screen. So for optimization problems, the idea is that we're usually given an equation. Sometimes it's an equation of volume, sometimes it's an equation of area, sometimes it's like a speed equation. Um, and the idea is that we want to sort of take the derivative of that equation and find the 0 points. And if we think of it just from a sort of graphical standpoint, so let's just say we have a graph of a random function. Let's say this function is represents an area function. So we say the area, and let's say it's with x. Um, so if our function looks something like this, um, maybe like this, we can see that our function has some sort of obvious max points and obvious min points here, just by looking at the graph. For example, right here, let's just call this x1, and right here, let's call it x2. And the important thing to note is that if we were to actually look at sort of the rates of change at this graph, like the slopes, like here, for example, a tangent slope at this point, or for example, a tangent slope at this point. If we look at the tangent slopes at our maximums, um, we see that they're horizontal lines, which means that our the slope of these tangent lines should be 0. Um, and remember that we get the slope of our tangent line by taking the derivative of the function. If we're talking about a specific tangent point at a certain point. Um, so uh, so uh, if uh, if we have this function, this area function, and we want to find this maximum points, therefore it makes logical sense to figure out where the derivatives are 0. Now it's also important to note that our minimum points also uh, have derivatives of 0, or sorry, yeah, derivatives of 0, slopes of 0, horizontal tangent lines. So when we do find solutions for these sort of problems, it's important that we need to figure out if it's indeed a maximization, or if our solution is actually a minimization for the problem. And of course, our problem text is going to tell us whether we need to maximize or minimize what we're looking for. So let's go through an actual example optimization problem. Let's say we have, let me clear this board. Um, is everyone seeing the board fine? Okay, it's lagging. Let's see if I can. Uh, oh, we'll try to continue with the whiteboard. And if it doesn't work, I guess we can try. The problem is like the e-learning's not letting me share the screen for my Paint application. Otherwise, I just switch to that. Um, well, let's continue. Let's see if it works. Um, so let's say we have a problem that states, let's say a farmer. Uh, Actually, yeah, now I'm having whiteboard issues as well. Uh, it might be the number of people connected. So let's say a farmer wants to build a cylindrical grain silo, uh, so that the uh, let's say the vertical cross section lies under the curve 40 minus 3x squared. What is the, say, the height of the silo that maximizes the volume, and what is that maximum volume? Okay, so right off the bat, we can see that this question is, well, the first thing that alerts us that this is an optimization question is, of course, the word maximize, right? When we have maximize or minimize in our question, that sort of alerts us to the fact that this is probably an optimization problem. Um, Sort of, I guess, another thing that might kind of tip us towards it being an optimization problem is the fact that not only do we talk about volume right here, but we also have a different equation that doesn't relate directly to the volume. So sort of an equation of a curve that will be used during the optimization process. And just one sort of, I guess, tip that I personally learned, one of my teachers from way back told me when I was studying for math tests, is during tests, I always find it pretty helpful to actually like underline parts of the question that I think are important and that'll help me with the question. So for example, we've underlined maximize, we've underlined volume, we've underlined this equation 40 minus 3x squared. And I think maybe the last thing I would probably underline is vertical cross section and maybe cylindrical as well. So let's think about all these pieces of information that we've been given. So we have a cylindrical silo, but the vertical cross section of that cylinder lies under the curve 40 minus 3x squared. Yeah, and that's definitely a good comment that there's often I guess like these problems are almost always word problems, right? And there's just a lot of like different things they say in the problem. So again, I think that underlining it might help sort of help you identify which parts are important. Yeah, so that's a good question. So what exactly does vertical cross section mean? So if we think of, for example, a cylinder, let me draw a cylinder. So let's not think of the cylinder as a silo. Let's think of the cylinder as a cake for a second. And let's imagine we have just a knife. And we bring this knife and we just cut our cake. But we cut it into this really, really thin piece. So it's just one slice of the cylinder. Essentially, if we drew a diameter on the top of the cylinder and brought that diameter all the way down to the end, to the bottom base of the cylinder, so I draw it like this, and all the way down to the other side. So it is half of the cylinder if we cut it, if we did this slice. But now we're talking about a cross section. So what this cross section means is we're just thinking about just this one slice, not even the whole half of the cylinder, but rather just this one slice that are sort of the path our knife takes as it cuts through the cylinder. Yeah, so it's related to the height exactly. So in essence, the reason we want to do cross sections is we're trying to sort of turn our 3D equation or our 3D problem into a 2D problem. And by getting this cross section, we essentially kind of turn our cylinder into a rectangle in this case. Because if you think about like the actual, think of the actual path of the knife. Imagine that we have a knife that can cut a super, super thin slice. And so it just cuts this sort of slice out like this right here. So if we cut that slice out, we just have now a rectangle. And let's draw a coordinate plane in this way. So 2 radius. Yeah, exactly. That's a good observation, right? So let's draw it like this. So this is our cross section now. So essentially, we've taken this part of our cake silo and put it on the actual Cartesian plane. So this is our, let's say this is our x, and let's say this is our y. Now, so like someone just mentioned in the comments, we can actually see sort of a relationship between these sort of, I guess, parts of the cross section. So if we just look at this part right here, and let's imagine that we've positioned it on the Cartesian plane so that it's divided exactly in half. That's to say that this area to the left of the y-axis is exactly the same as the area to the right of the y-axis. So we essentially taken this rectangular cross section and split it into two parts, two equal parts rather. So what we can do then is if we just consider this part now, um, so So no matter how you cut it, the height will be the same, right? But it's important to note that in optimization problems, we don't know exactly what the height is yet. So we're gonna be like sort of making our height bigger or smaller. So depending on what the height of the cylinder is, the height of the cross section will change, right? And we don't know exactly what that height is. Yeah, exactly. So half of the diameter is on the left and half is on the right. We essentially, if you can think of it, this top part of this cross section is going to be this just full top part right here. And of course, half of our diameter is our radius, right? So if we just look in our positive quadrant, this part that sticks out of the rectangle, the width rather, of this rectangle in the positive quadrant, quadrant one, is just going to be our radius of our cylinder. And this part right here is just going to be h, which is the height of our cylinder. Now, it's sort of, I guess, one of the other things we need to remember is uh, we need to sort of get the volume equation for our cylinder, right? Because we're going to be thinking about volume, we're going to be maximizing our volume. So our volume equation for our cylinder is V equals pi r squared h, where r is the radius of a base of the cylinder, and h is the height of the cylinder. Um, so uh, So the problem is if we try to take a derivative of this right away, we have two variables here, right? We have an r and we have an h. So since we don't right now know the relationship between h and r, we can't exactly take the derivative because we don't know what to do exactly with h when we try to take the derivative of h with respect to r, or we can't take the derivative of r with respect to h because, again, we don't know how the two are sort of related. And that's, I think, one of the major key or crucial steps of the optimization problem is that, generally speaking, you're going to be given a formula where you can write it in multiple variables. And so like this. And we need to change this so that this volume equation becomes an equation of simply one variable. And in order to do that, we're going to sort of need this other equation, this 40 minus 3x squared. Now, I know that I've sort of said a lot right now, and there's a lot written on the screen right now. So I'll give you guys just a little while, like a couple seconds to sort of take it all in, because I'll have to clear my screen in a second. But the important parts are the important parts that we're going to use now is we're going to use this sort of cross-section diagram we have right here. We're going to use this volume equation we derived for the, or we found, or we know, sorry, for the cylinder. And then we're going to use this curve equation because we haven't actually plotted this curve or used this curve yet, right? Yeah, an easy way to remember the sort of the cylinder formula is, so if we have a cylinder, you can sort of think of it like a stack of disks, right? And one of our disks is just the base, right? So if we calculate the area of the base, that's pi r squared. And you have like a h number of disks, essentially, a height number of disks. So you just take that area of one disk and you multiply that by the height. Okay, with all that down, I'm gonna clear the whiteboard. Okay, so let's think of this equation now. Um, 40 minus 3x squared. Um, so 40 minus 3x squared is a parabola, and it's opening down. Um, one other thing I want to mention to y'all, I know it sort of sounds like a lot of complicated terms like vertical cross section, um, or just cross section in general. But generally speaking, a lot of these problems will give you a diagram, so you'll probably get that vertical cross section diagram before in the problem. So you don't have to sort of, I guess, know what that means or derive that right away. Um, like almost every optimization problem has some sort of pictorial aid, especially on tests, to help you sort of visualize what's going on. Um, but let's go back to this equation we have right here. 40 minus 3x squared. So this is a parabola. It's opening down. Our y-intercept when x is 0 is at 40. Um, and it sort of goes down like this and like this. So when we say the vertical, or sorry, the vertical cross section of the silo has to lie underneath this curve, what we're saying essentially is that, for example, if we draw a vertical cross section, so you can see that the whole vertical cross section lies underneath the curve, and we have these sort of intersection points right here. Um, but it's important to note, right? We have essentially an infinite number of ways that we can put this vertical cross section under the curve, because again, we don't know what the height is. We haven't specified a specific height yet for the silo. So like another possible way is to simply do uh, 1 second. Oh yeah, sorry, my pen sometimes doesn't work on the whiteboard. Um, yeah, so that's a good point. Um, if you sort of like, yeah, that's a good point that sometimes they're cylinders with an actual like semicircle dome on the top. And I guess generally if you like work it out that way and your professor sees that you actually like did more work than was necessary, but your I guess initial starting point makes sense, then I'm sure that they'll be lenient with the points. I mean, obviously I can't speak exactly for the professor. But again, most of these questions will have some picture alongside them to help you understand. Uh, this I might need to reconnect for my, sorry. Uh, so again, I don't know exactly how your professor is going to run the exam. I haven't seen the exam personally. I just, from my experience of having taken tests like these, usually um, there's a picture that goes along with these optimization problems. But looking at this again, I just to show, sorry, to show another example for a possible optimize or a possible cylinder under the uh, curve, we could have, for example, something that looks like this. A much smaller height, but a larger width. And sort of what we need to now recognize is what sort of information does this curve give us? And for that, I think we should just look at the positive quadrant one. Because one thing to do in a lot of these questions is to see if there's any symmetry. So for example, if we look at this picture or any of these two pictures, we see that there's symmetry across the y-axis. Um, so 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 we see that if we like look at the left side of the quadrant two, or we look at quadrant one, the figures are exactly the same. They're just flipped over the y-axis. So essentially that allows us to just look at one half of the sort of the coordinate plane. So if we just look at, for example, the positive half like this. Remember, we're trying to figure out if there's a relationship between this height and this. Sure, I can try. Uh, so we try with this. Yeah, I apologize. I think it shows up a little different on different people's screens. So is this work better for you? So we have it like this. Yeah, so we have this height h and we have this width. We'll call it r because this is still the radius of the sort of uh, the radius of the cylinder. Sorry. Um, And remember now, the important thing we need to note is that this corner point right here is an intersection point between the curve and the silo. Because otherwise it wouldn't make sense for us to sort of put the silo in the middle while there's still some space remaining. That wouldn't maximize our volume then. So this corner point right here should be an intersection between our curve going down and the cylindrical corner. So if we think about that point, um, so if we think about what actually the x coordinate of that point is, we see because this bottom part is the distance r, or the width is r, the x value at this point should be r. And if the x value at that point is r, we can calculate what this by simply doing uh, uh, r comma and now we have our equation. So let's say we call this equation f of x, f of r. Um, so the idea is that because this point, yeah, sure. So the idea is because this point sort of lies uh, on the curve. If it's at x coordinate r, the y coordinate should be f of r because it lies on the curve f of x. So there was a question, why am I only solving it for the first coordinate? So if we look at the symmetry for the system, if I solved, for example, for this point right here, we should get the exact same thing. It's just going to be flipped over, right? So instead of r, this time it'll just be negative r. But our f of r should be the same value because this is a quadratic equation. So for a quadratic equation, right, if we have a positive or a negative, it should stay the same. So if we actually sort of see how these are related now, so that means our f of r, our h, switch back to 5, interesting. So we get our h equals 40 minus 3 r squared now, because this is f of r. Instead of x, we're plugging r in. So now our volume we can write as v equals pi r squared h equals pi r squared 40 minus 3 r squared. And now, since we have our volume only in terms of one variable, we can take the derivative of this and set it equal to 0, right, to get our optimization. So we get dv dr is equal to, so let's quickly just distribute this pi r squared. So we get 40 pi r squared minus 3 pi r cubed. So this is going to equal 80 pi r minus 9 pi r squared. And we're going to set this equal to 0. So we can just factor out our r now. So we get r 3r to the 4. Oh yeah, sorry. Yeah, sorry. This should be r to the 4. Because yeah, right. Because r squared times r squared is r to the 4. My bad. So this becomes a r cubed. So we get r times 80 pi minus 9 pi r squared equals 0. Now this gives us two solutions if we go out and solve it. Technically three solutions. So we have r negative. It should be yeah, because now we bring down the 4, right, instead of yeah. No, it is. You guys are right. Apologize. So this will be 12. This right here is also 12. So we get either r equals 0 just from this r that's being multiplied outside, or so we get 80 pi minus 12 pi r squared equals 0. And if we solve the second equation, so I got the equation for height because it's lies on this curve that we gave, this curve right here. So if we solve our second equation, we get r equals square root of 80 over 12, and this plus or minus. So now we have three things to think about. Okay, can r equal 0? Well, if r equals 0, that's just looking at a cylinder that's not really a cylinder. It's just a line then, right? It has no width, and therefore the volume is 0. And that's actually our minimized solution. So that's not what we're looking for. Now we can think of r equals positive 80 over 12 or negative 80 over 12. But like I said before, those are the exact same solutions. R is positive 80 over 12. Is just looking at the right side of our equation of our sorry, the right side of our diagram, and then negative root 80 over 12 is just looking at the left side of our diagram. So we can pick either value because when we substitute that back into f of x, we'll get the same answer. Yeah, you can simplify it just by dividing top and bottom by 4. So we could say root 20 over 3, and then you can plug that back into your equation to get your actual height. And it'll be so you could do like 40 minus 3, and then so this 20 over 3 becomes, or this root 20 over 3 is squared, so it just becomes 20 over 3. And that should just give us 20 as our height. And then just calculate the volume by plugging this r into this equation right here, pi r squared 40 minus root 3 r squared. Or since we already found the height, essentially it'll be v equals pi root 20 over 3 square minus or times, sorry, 20. And that'll give you your maximum volume, which should be like pi, I think 20 squared over 3. So definitely a lot of steps, and I'm sure y'all were asking for optimization problems because those do tend to be pretty long problems. Definitely a lot of places to get tripped up. You all saw me get tripped up doing the derivatives. But essentially the main points of the optimization problem is figure out what exactly we're optimizing, so the formula that we're trying to optimize. And usually it's going to be a multivariable formula. So figure out how we can relate those variables together. Sort of just by analyzing maybe like a graph or a picture of sort of what the problem is asking. And once you relate them together, you can turn your original equation into an equation of one variable, like we did for volume here, as just an equation of r. Take a derivative with respect to that one variable, and set that equal to 0. And then you'll be able to solve for that one variable, optimizing that one variable. How do we know which variable to isolate? So generally speaking, you can check your you can check your variable, or you can isolate either variable. It's just in certain cases, it's easier to isolate one variable than the other. For this example, I decided to solve for h instead of solving for r, because if you solve for r in terms of h, once you plug that back into this equation, this v equals pi r squared h, you're gonna have like some term, like some function of r squared, or sorry, some function of h squared, and that's gonna be sort of difficult. How do I get h equals 20? So we found that the maximum r is root 20 over 3, and we found that our height equation is modeled by this f of x equation right here. So I just plugged root 20 over 3 into that f of x equation. So actually, there's no difference in most of the steps between solving for a minimum or a maximum. And like we saw right here, when we solve for our maximum, we also find our minimum. Um, So like right here, we found this r equals 0 is technically a minimum, because that's just the zero volume thing. Um, so so once you actually find your critical points, you have to test if they're maximums or minimums. Um, so we found the radius by optimizing this volume equation, because we wrote this volume equation as an equation only of the radius right here. Um, And once we were able to take the derivative of that and set it equal to 0 right here, we were able to solve for r, and that r was the radius for our maximum volume. And also important to note, like we mentioned before, we have to think of our extrema points, or where the horizontal line, our tangent line, is going to have a 0 slope, and those are going to correspond to 0 values now in our f double prime, right? Because again, our f double prime is the slope of f prime. So between 1 and 1/2, we kind of have this arc, because we're positive the whole time, but we're positive increasing steeply, and then sort of start decreasing in our steepness of our slope. So instead of thinking of the actual values, like the location above or below the x-axis, think of the slopes when we're trying to convert from both from f to f prime and from f prime to f double prime. So we go like this. Now, if we look between -2 and this -1/2, again, at -2, we're going to have a 0. So our 0 is going to look something like this. And we have a negative graph that's, again, sort of, it's starting off steep and then ending up less steep. So once again, it's going to look sort of, and you can like kind of look at these graphs and see how like between -1/2 and 1, and between 1 and, or sorry, -1/2 and -2, we kind of have a reflected graph, right? So our f double prime graph should look reflected too. So I'm not sure if you'll have direct graphing between them, but you'll probably have to, yeah, you'll probably have to sort of correlate like graphs together, maybe. Like sort of say like if this is f, which one of these makes sense as the f prime graph, or like given f, maybe sort of figure out the important points of f prime. And then finally, if we look here, our slope is positive again. So we're positive again, but as we go to negative infinity, our slope like decreases, positive but decreasing. So something like this. And this is how our f double prime graph is going to look like. Now, sometimes, like you mentioned, you might just be given the f double prime graph. Sometimes you kind of have to just see how the behaviors correlate between these two graphs. I don't know if you're going to have to specifically graph out the f prime versus f double prime, or like get the f double prime from f prime. But it's definitely good practice because the same idea holds true if you're going from f to f prime, right? It's the same concept, the same things to look out for. Figuring out where the 0 points are, figuring out where our graph goes positive, where our graph goes negative because of the slopes. So now that we figured out what our f double prime actually is, we can figure out our areas of concavity, right? Um, so if we look from 1 to infinity, we're at 0, right? And at 0, when f double prime is at 0, there's no concavity. So we can't say that f of x has a concavity from 1 to infinity. Now from negative 1/2 to 1, we have a positive second derivative, which corresponds to an upwards concavity, right? And the same thing from negative infinity to negative 2. So we can say, sorry, I can't use close brackets here. Say open brackets, negative infinity, negative 2, union, negative 1/2, 1. That's our upward. Then our downward is negative 2 to negative 1/2. Now, it was very important that we use open parentheses, or open brackets, I guess, for all of these sets, because at the points where f double prime is 0, our concavity is neither up nor down. Those are our inflection points, right? And so therefore, at those points, we can't exactly, our graph is neither concave up or concave down because it's kind of both at the same time, right? Or neither in some cases. So that's why we don't include those points in our actual intervals. So yeah, so that's our first part. And our second part is sort of doing the reverse logic. So you said usually you're given functions. So you're given functions and then you get like f prime given like f. Is that usually how it goes? Okay, yeah. So the important thing to note is going from f to f prime is exactly the same thing as going from f prime to f double prime, like graphing wise. Like because like the relationship between f prime to f double prime is a derivative and the relationship between f to f prime is a derivative, I could have like just like erased like a single prime from both of these. So it would have just been f of x and f prime of x. And the graphing sort of technique would have looked exactly the same. Um, the important part to remember is it's just that the graphs like have different effects on f, right? So so because this is a f double prime graph, it's talking about concavity. Because this is a f prime graph, it's talking about the slope of x. But otherwise, when you compare them to each other, the methods of moving from one to the other are exactly the same. Yeah. Okay. So usually it's like so you're given uh so this is less of the graphing stuff and more of just then solving out the derivative, right? Um, so like for example, I guess I think actually there's an example here. Yeah. Yeah. So the important part to note is like say for example like um let's just do an example like this. Say we get like a rational function derivative. And say wait, yeah, I don't know why for some reason my the tablet thing uh doesn't work sometimes. So Say for example, we get the rational derivative f prime x equals, let's say x plus 2, x minus 1 over x plus 4, 2x minus, let's say 5. From here we can sort of draw out our number line, right? And think about all the critical points, or potential critical points rather, that lie on it. So from this x plus 2, we get negative 2, we get 1, we get, actually, I'll replace this with a negative 4. I'll put a negative 2 here. And then we get, actually, we got 1 and 5 halves. So some of these are asymptotes, right? And some of these are actually the 0 points of the derivative. So we can sort of mark them. So our 5 halves and our negative 4 come from the denominator. So when those happen, our denominator is 0 and we get an asymptote. So D and E. And then these points are 0 points. Now you talk about plugging in, and I'm assuming what you mean by that is plugging in like sample like values or representative values and seeing what the sign is then of the derivative, right? So for example, like we want a sample value greater than 5 halves. So 5 halves is a little less than 3, right? So we can plug in 3. If we plug in 3, we get 3 plus 2, 3 minus 1, 3 plus 7, 6 minus 5. So this is a positive number, positive number, positive number, positive number. So right here, we get a positive in this interval. Now from 1 to 5 halves, an example we could do is, for example, 3 halves lies below it. So we do 3 halves plus 2, 3 halves minus 1, 3 halves plus 4. This is 3 minus 5. So again, positive, 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 but this time negative. So we get a negative here. The important thing to note here is we don't actually have to actually solve out what it is each time. Going over finding the point on a line closest to origin or another point. Finding the point on a line. Oh, this is like an optimization problem for a distance. Yeah, we can do that in a sec. So then between negative 2 and 1, like for example, we can do a representative value of 0. So we'll get 0 plus 2, 0 minus 1, 0 plus 7, 0 minus 5. So positive, negative, positive, negative will give us a negative over a negative, which will be a positive. So it's a positive. And essentially you can keep on plugging points and you'll find that it should switch over like this. And the idea is that now that you have these sort of positive and negatives, like you know that these are your critical values already because these are where the derivative is 0. You can see that these also form certain like maxes or mins, right? So for example, if we're going from negative to positive, it's sort of a negative slope to a positive slope. That should be a minimum. And that should also hint us that we're at a concave up part. If we look at around 1, we go from a positive slope to a negative slope, which is a maximum, and that hints us that we have a concave down. Now, of course, you could go one step further and actually calculate f double prime x and do the same sort of plugging in representative values. But the idea is that even from the first derivative, you can sort of get sort of clues or hints as to where we are concave up and where we're concave down. Um, so we can try doing the finding a point on a line closest to the origin or another point if you all want. Um, and let's say let me erase this. Um, so let's say, for example, we have a curve f of x equals, let's say, 3x squared plus 2x. And we want to find, actually, let's just make it plus 2. And we want to find where this is closest to the point. Let's do the point 4 comma 5. So we want to find that and we're finding a pointer, so we're gonna need an answer in a coordinate pair. Um, so one thing we can think about, again, because this is an optimization problem now, what sort of, you can think of like a physical quantity, or what quantity are we trying to optimize? And in this case, we're trying to optimize a distance, right? So I'll say, and optimize distance, but more specifically, minimize it. Um, and we know from our distance formula, if we have, let's say, points x comma y, and we're trying to compare the distance to 4 comma 5, our distance formula will simply be x minus 4 squared plus y minus 5 squared. This is our distance formula, right? Um, now, because we're specifically on this curve, this 3x squared plus 2, we're looking at points on this curve, we want to sort of, again, and I'm going to write this is our distance formula, so let's just call this equals r. We want to turn this formula into a formula of only one variable, because again, then we can take the derivative of both sides, set it equal to 0, and figure out for one variable. So for any point on this curve, our coordinates for that point are going to be x comma f of x. Or for just a sample point A, we'd have a comma f of a. But we can see our y value for any point is given by f of x, right? That's sort of the definition of a point being on a curve. It follows the equation of the curve for the y value. Which means if we're at some point x, we can just replace y with f of x. So we get root x minus 4 squared plus f of x minus 5 squared equals r. And then we get so here we can get, yeah, I'll do that in a sec. Good comment. But first I just wanted to sort of write out what f of x is, just so root x minus 4 squared plus 3x squared minus 3 squared equals r. So now what Les is saying, and what actually people were saying earlier in the lecture when I was doing a problem kind of similar to this, is that instead of optimizing the function r, we can actually think about optimizing the function r squared. Because if we think about it as r itself gets smaller, r squared also gets smaller the same way. Or another way of thinking about it is um, optimizing r, or optimizing the distance, is the same thing as optimizing the distance squared. Whatever value is going to have a shortest distance is also going to have the shortest distance squared. Because essentially the squaring it doesn't affect sort of you can think of it like the length, because, and this is the reason for this, is because all of our r's are supposed to be positive. We can only have positive distances. So if for example, if A is greater than B, then it's necessarily true that A squared is greater than B squared. So optimizing R squared is exactly the same thing as optimizing R when it comes into terms of solving out our answer. So if we square both sides now, we get x minus 4 plus 3x squared minus, sorry, this is squared, equals, and let's call our objective function, let's call it f now, which is the same thing as R squared. And remember, we're taking the derivative of f now, because f is our new objective function. So we don't have to worry about, implicitly deriving this like 2r dr. So what we can do now is, let me sort of erase some things here. Yeah, it's an important note also greater than 0, right? Because we're talking, in this case, we're talking about distances. So our A and our B are going to be positive, greater than 0. So in this case, we get 2 x for our sorry 2x minus 4, and the derivative of the inside is just 1, right? Because the derivative of x minus 4 is just 1. I'm taking the derivative of both sides of this equation now. So I'll write that here. So df dx equals 2x plus 2 3x squared minus 3 times 6x. And we have to set this equal to 0, right? So therefore we get 2x minus 8 plus, now multiplying. So this is essentially 12x, right? We can multiply by 12x squared, so plus 36x cubed minus 36x equals 0. Now, in this case, with the sort of the random points I chose, we'd have to like do a synthetic division or do some numerical method, maybe like just looking at the calculator graph or guessing values to sort of solve what the values of x were. But like, so we have 36x cubed minus 34x minus 8 equals 0. Suppose that we were able to solve ln. I don't think ln would really help us here. The point is like, because we have this constant term here, we can't exactly like factor out an x. But like imagine if instead of this being minus 8, suppose this way. Suppose instead of going from 4 comma 5, we go from sorry, I'm changing the problem a little bit, but we do it to the distance 0 comma 5. Then our x here is just going to be 0. You can just put minus 0, minus 0, minus 0, minus 0. So our derivative will just be a derivative of x squared, which will just give us 2x. And this minus 8 term will essentially just disappear. So we'll just be left with 36x cubed minus 34x equals 0. So we have x 36x squared minus 34 equals 0. So this gives us x equals 0, or 36x squared minus 34 equals 0. So this is x equals 0 still, or x equals plus or minus root 34 over 36. And if we sort of think of our sort of how our graph would look like, so we have a point. I basically just manipulated the equation. I like changed it, so instead of going from 0 or 4 comma 5, like the distance to 4 comma 5, I just had to change it to 0 comma 5 so that 4 disappeared. So there's no more minus 8 term. I just changed the problem essentially so we could take away the minus 8 and make it easier to solve. Um, so our 0, 5 is like here, and our parabola sort of goes up like this. So just looking at it graphically, we can see that there isn't actually going to be any maximum value um, when it comes to distance, because like we can always find a further point away from this 0 comma 5 point. But we can see it's sort of like, you can think of it kind of like a semicircle around that point. There's going to be 3 points here, which all should be equidistant from this one point in the middle, 0 comma 5. And those are given by these x values. X equals 0 minus root 34 over 36 and root 34 over 36. Now, if if um, if we're being more rigorous, we should do like, sorry, for example, the first derivative test or second derivative test, to make sure that these are actually indeed minimums. But sometimes, just like for the sake of time, I'm just showing you how graphically we can see that logically these 3 points have to be minimums. And then to find the y values, we would just plug them in to this f of x equation, right? So if we plug in 0, we get the point 0 comma 2. If we plug in negative or root 34 over 36 or negative root 34 over 36, you'll see that they give the same f of x value because we have an x squared. So we'll get, I believe we get, so it's 3 times, so it'll be like root 34, 36, 34 over 12 was like 58 over 12. And then the same thing, so I'll just put plus or minus. And if you calculate your distances, I think you should find that all of these are 3, distance 3 from those points 0 comma 5. But the really important part in doing these distance from a point questions, optimization questions, is to first derive our distance equation, like right here. Then note, just as Liz said, we can change our objective function from, instead of being just r, to being r squared. And then, so we change it to r squared to get rid of this square root that's at the top. And once we have our objective function that's r squared, we just take the derivative of that. Remembering that for our y value, we can just substitute in the equation of the actual curve. And we just take the derivative and set it equal to 0, because once again, we have a function of only one variable. And then we can use that to solve for our x. And depending on our graph, like, we're sometimes only guaranteed to have minimized values, like in this case. So does that make sense? All right. Well, I think the final solution is right here, these 3 values. You can simplify the bottom values, but it's um, like they should be the same, equivalent. You can just simplify the fractions a little bit, right? But essentially, from these 3 x values we found, we just plug them into this f of x right here, and that gives us our 3 coordinate pairs. I just, to save space, like combine 2 coordinate pairs together, so our positive root 34 over 36 and our negative root 34 over 36 share the same y value. That's why I put the plus or minus there. Yeah, so all three of these points are the same distance away from this point 0, comma 5. Um, and it makes sense that these have to be the closest, right? Because there's no way to calculate the furthest point. Because the parabola goes into infinity, um, any point that we could try to find a distance for, there'll always be another point that's farther away. So these have to be the three closest points. So the diagram I drew in the middle, it's kind of hard to see, but it's like 0, comma 5 is right here. Our vertex is 0, comma 2, which is one of the points we got. And then on the sides here and here are the root 34 over 36 solutions. And it makes sense that we should have two solutions with the same x values, just flipped signs, because our parabola is symmetric, right? So yeah, exactly. So you could use your second derivative check to make sure they're actually the closest ones. I just, for the sake of time, I just showed the graphical interpretation or graphical proof that these have to be the closest. But yeah, and I actually like, um, I'm sure your professor would make you do this too, where you should show using a second derivative test that this is indeed minimum points, or with the first derivative sign chart. Okay, I know that y'all wanted to do some more optimization problems. I know this is another optimization problem. Um, I think unless somebody has any other topic they really want to go over, we can do another optimization problem. But if someone has anything else, feel free to ask. Okay. Um, so let's do this optimization problem, sort of similar to the planes problem someone was mentioning earlier. And it's in the problem set. It should be or sorry, I guess the plane one was a related rates question. If we want to do optimization, we can do uh, well, I guess we can do the triangle and the square one, because that one has like an interesting sort of conclusion to it. Um, so idea is we have an equilateral triangle and an equilateral square. Sorry, I guess a square is by definition equilateral. Um, and the idea is that um, we have, so the both of these are like made out of wire, and the total amount of wire is still not working. So the total amount of wire is 9 feet. And we want to find the side length of the square that maximizes the total area, surface area of these two objects. Um, so what we can do is, well, first of all, let's call our squares x and x, and let's call our triangle sides S, S, S. Um, and the first thing we have to note, because these are equilateral, both of these, all of these sides have to be X, and all of these sides have to be S. They all have to essentially be the same side. But it's important to note that S and X don't have to be equal, right? The side lengths of a triangle don't have to be the same as the side length of our square. Um, but what we do know is 3S plus 4X equals 9. Because that's our on our left hand side is the total amount of wire, and the right hand side is the total amount of wire they gave us. So equation to calculate the total amount of wire, and then the right side is the actual constraint. Um, and what we can see then, for example, is so we want to find the side length of the square, which means X is probably more important to us than S is. Or I guess we want to solve for X as opposed to solving first for S. Um, and we also need to figure out what exactly our total area formula is, right? Because again, whenever we have an optimization problem, we need to figure out what it is exactly we're optimizing. So in this case, total area. So our area equals, so our area for our square is simply x squared. Plus, and now our area for our triangle they gave us is root 3 over 4 s squared. Okay, so we have our area function. We want to optimize it. Again, we run into the problem that we have two different variables, x squared and s squared. But once again, we have this different other equation that we can use to sort of convert our multivariable equation for area into a single variable equation. And again, since we said we wanted to solve for side length, let's solve this equation in terms of x. Sorry, side length specifically of the square. Um, so if we do that, we get 4x equals 9 minus 3s. Oh, sorry. In this case, I guess we wouldn't be solving for x. We'd be solving for s because we want to replace um, the s in our area equation with an x, so that our area equation only becomes a function of x. So we get 3s equals 9 minus 4x for s equals, so 9 divided by 3 is just 3, and then minus 4 over 3x. Now we can sort of plug this s now into our area equation. We get area equals x squared plus root 3 over 4, 3 minus 4 thirds x squared. Um, and now we can sort of take the derivative on both sides. And remember, we have to set our derivative equal to 0 in our optimization problems. So dA dx equals 2x plus root 3 over 4 times 2, 3 minus 4 over 3x times negative 4 over 3. I'm just doing our chain rule. I mean, technically speaking, I could have expanded this out also and done the derivative that way. Either method's fine. Um, so, and remember that this has to equal 0 because this is our optimization problem. So therefore we get 2x plus, and I'm going to combine sort of all these different multiples, this one, and this one together. So these 4's will cancel out. And we have a negative sign, so there should be a minus here. Minus 2 root 3 over 3, 3 minus 4 thirds x. Okay, and again, this still equals 0. And now we can do, so we just distribute this 2 root 3 over 3 to our different parts right here. So we get 2x minus 2 root 3 plus 4/3 x equals 0. Therefore, we get 10/3 x minus 2√3 equals 0. I believe. Let me just check to make sure. Huh, wait. Yeah, I believe this is right. Let me just so 4's 2, 3. Yeah, I believe this is right. So therefore we get 10/3 equals 2√3. Sorry, 10/3 x equals 2√3. You get x equals 6√3/10, which is 3√3/5. So we got this equation, but now what we need to think about is so 10. Yeah. So what we need to think about now is so we got x equals 3√3/5, and it seems great because we only got one solution. But the important thing that we always need to do in optimization problems, something I've sort of been skipping, but this time I won't skip, is doing our second derivative test, right? So this time when we do our second derivative test, we find our first derivative right here in our simplest form is like this. So if we do our second derivative test, let me erase some of this stuff. Oh, 100%. All right. So this is s equals 3 minus 4/3x. When we do our second derivative test, we find out that our second derivative is, so let's say 10/3x minus 2√3. Derivative is actually 10/3, right? Which is a positive number. So that means our second derivative at any x value, but even at the x value we're interested in, is a positive, which is concave concave up, right? So if we have concave up, remember how concave up kind of looks like this. So if we have concave up and we find a critical point, we actually have found a minimum. So we found the minimum area of these two sort of shapes with this x. And our problem asked us to maximize it. So this is an example where, because we found a minimum, we're going to have to think of our boundary conditions now. So our boundary conditions are either we give all of our wire over to this triangle, or we give all of our wire over to the square. So let's suppose, let me just clear it. So we have our triangle, S, and our square, X, 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 X. If we give all of our wire to our triangle, our area will just become √3/4 times 3 squared equals 9/4 √3. If we give it all to our rectangle, or sorry, our square, we'll get 9/4, because we have to divide our 9 feet equally among all four sides, squared equals 9/4 times 9/4. Now, if you look at this, this is √3, this is 9/4. You can look at your calculator also, but √3 is about 1 point something. 9/4 is greater than 2. So this second number is greater than the first number, and because there are boundary points and we're going concave up, one of these two has to be our maximum, right? So if we looked at how like a concave up graph looks like, something like this. So wherever we restrict it, one of these two restrictions has to be our maximum value. And both of these have to be greater than our minimum value, greater than or equal to our minimum values. For concave up, greater than our minimum value. So we find the actual way to maximize this is to give all of the material over to the square. And the point of this problem really is to show you the importance of doing a second derivative test. Sometimes we'll do an optimization problem and find out, oh, there's only one answer, so that must be the correct answer. But it's always important to check whether you're actually really maximizing or you ended up accidentally minimizing. Um, So I know like sort of came out as like a long ramble of a bunch of different steps, but the main idea was we solved our optimization problem regularly, like we solved all the other optimization problems, figuring out what equation we need to optimize, figuring out the relationship between two variables, solving for one variable, and then plugging that into our equation to optimize, and then essentially uh, essentially getting a value by setting the derivative of that equation to 0. Um, but this is a trick question where that value isn't actually a correct value, and we have to use our second derivative test to show that that's not the correct value. That isn't the correct value we should be looking at, and instead we should be looking at boundary values. Yeah, so does anyone have any questions about this one? Any time-saving tips for taking an exam? I think the one that a lot of people talk about is if you get stuck on a problem, like move on to the next problem. Personally, for me, I'm not sure how long is y'all's exam, and do you know how many questions you have? They're usually like I remember like my calculus test would be like around 2 hours for 5 questions. I don't know if it's the same for y'all. Um, but personally, when 8 questions. Wow, that's a lot. I don't remember having that many questions. But okay, yeah. So especially with 8 questions, then, um, I mean, y'all are coming here. Y'all are clearly studying. There's got to be wow. There's got to be some questions that you're really comfortable with, and then some questions maybe you're less comfortable with. So personally, I tend to go through, um, and like try solving all of them, and then once I like realize this is kind of a hard question, I move on to the next one and see if that's easier. If that's easier, I finish that one first, and then I go back to my hard one. So definitely um I think not really a time save. Well, it's kind of a time saving. So instead of just hitting your head against a wall in one question, maybe move on to another question. I think another thing that personally helps me a lot is sort of to think of the logic of my answers or what I expect my answers to be. Um, like for example, for that distance problem we were talking about, if you actually just like think of the graph, and I'll just draw it again. So think of a graph of a parabola with some point on the y-axis. It seems very logical that there should be 3 points, um, at least 2 points, maybe even 3 points that all are equidistant to that point. So it would make sense to me to find 3 answers. Um, but of course, still make sure that those are minimums. For a question like this, for example, when I realized that the middle point that we got was a minimum, I think it would logically make sense to me that giving the wire to the square would be larger than giving it to the triangle. Um, you still have to, of course, go through all of it, but sometimes it can just help you get a little faster when you know sort of what you're looking for. Um, and another thing is like uh, even if you think you've forgotten, like for example, some identity, like we were talking about earlier, for example, you forget limit x approaches 0 of sine x over x is equal to 1. Um, there are almost always ways that you can use the knowledge you have to sort of rederive them. So like for example, for this, you can just use your L'Hopital knowledge to sort of rederive this identity rather quickly. Um, so I guess yeah, I guess those are my basic tips. Just like make sure you go through the whole test definitely before you get stuck on one question. Just make sure you understand okay, what exactly are is on this test. I mean like during the test, like make sure you know what all the questions cover, so you know which questions you should probably target first. Okay, so I think we have time for one more question. I believe it's supposed to go to like 10:30. So if you'll want, we can do that related rates question I was talking about with the boats. Because that's kind of an interesting question. So um, this question is a 3.9b, by the way, if you have the problem set opened up. But the idea is that we have two boats in our XY plane. Um, we can sort of imagine the something like sorry, I apologize for constantly having to rejoin. I don't know what the some tech issue on my end. But so the idea is that we have two boats, and imagine we're like looking down at these boats and we're seeing their motion across the a 2D plane. Um, and sort of so for example, it's kind of like this is just kind of an example of the path. This isn't the exact path the boats will be taking. But we have both boat sort of A going like this and boat B going like this. And you can see as time goes on and these boats move go their own paths, the distance between these two boats will be changing, right? In this case, from the way I drew it, it seems like the distance between the two boats will be getting greater and greater. Um, and we're also given sort of the equations for each of the boat's movements. So for boat A, right here, um, so A, we're given that x A um, is equal to 2t squared, and y A is equal to 3t plus 5. And then for both B, we're also given x and y equations. We're given xb is equal to 4t plus 2, and yb is equal to 5t squared plus 2t. So four different equations, and this can definitely look scary now because we're gonna have to do a related rates regarding four different equations, and if you think about it, a bunch of different variables. But the good news is we can sort of kind of create some new functions that will actually simplify, or new variables you can think of, or functions that will simplify our related rates problem. Um, so um, so again, and in this sort of way, related rates and optimization problems are kind of similar. We generally want to have an equation in both of them that either we A optimize or B use to relate our rates. And in both cases, we're going to be differentiating this equation. Um, so in this case, we're talking about the total distance between boat A and boat B. Um, so So like this, that would be like this distance d in this specific instance. Um, and recall if we have the points, let's say um, a comma b, c comma d, our distance call it r is equal to square root of c minus a squared plus d minus b squared. And this comes directly from our Pythagorean theorem, right? If we drew like a line connecting our x components and a line connecting our y components, we'd have a right triangle, and we could calculate the distance, which is the hypotenuse of that right triangle, using Pythagorean theorem. Um, Now, if we talk about specifically the distance for our boats, we have r equals square root, and this time we have x a minus xb squared plus ya minus yb squared. So, in this case, again, we still have four variables inside our right-hand side of our equation, but let's sort of create two new functions. Let's create a function x, which equals just xa minus xb, and a function y, which equals ya minus yb. Sort of to simplify our equation and make us worry about just less stuff, I guess, in general. So r equals square root now of x squared plus y squared. And we can actually even solve out explicitly what these x and these y formula are, because we were given, right, xa, xb, ya, yb. So x will be xa minus xb, so 2t squared minus 4t minus 2. Y will be 3t minus 2t, so just t, plus 5 minus 5t squared. Um, so we can sort of essentially, so now that we're given our y and our x, um, which are both functions of t now, we can see very clearly both of these are functions of t. Um, we can do our implicit differentiation for this equation on the left. But again, we're going to do what we've been doing with all these sort of distance equations. And instead of just thinking of the distance, we're going to think of the distance squared. Um, so we're going to have r squared equals x squared plus y squared. Because again, these two equations are equivalent. All we did was square both sides, which we're allowed to do, a legal move. And the reason we want to do this, of course, is it makes our implicit differentiation a lot more, I guess, bearable. Um, um, I think one other thing maybe we were given. Yeah, sorry. One thing I forgot to mention. Another thing we were given is our dx dt is equal to 20. And it's necessary we need one of our rates of changes in order to sort of solve t plus 5. Yeah, t plus 5 minus 5t squared, right? That's sort of what I meant to write out. Just kind of, yeah, sorry. That was a little bit messy. That was a t. T plus 5 minus 5t squared. My bad. Um, so, um, what we want to think about is, so, and this is kind of, how to put it? Hmm. I think maybe in this case, we don't, maybe doing r squared might just lead to a little bit more work, because when we take our derivative, we'll have 2r, and then we have to calculate r as well, which isn't impossible, but it's a bit, well, Let's leave it as it is. Let's leave it as is. So we have all our pieces to a puzzle. Now we have to put them together. I guess one other step we have to do is take our implicit differentiation of both sides of our equation right here. So we get 2r dr dt equals 2x dx dt plus 2y dy dt. Now we have a lot of unknowns right now. In fact, we don't know anything except dx dt if we were trying to plug into this equation. But knowing dx dt is actually rather powerful for us because, and let me, let me just let you all take a screenshot if you want before I clear the screen. So there's no more room left. But dx, the reason I say, and I'm going to write that other equation we need to, so our two things we know is dx dt equals 20, and that 2r dr dt equals 2x dx dt plus 2y dy dt. And let's remember our x equation, our x and y equation. So x equals 2t squared minus 4t minus 2. Y equals, this time I'm going to just write out our t squared term first. Negative 5t squared plus t plus 5. Okay, and the reason I say this dx dt is very powerful is because we have x. So we can actually take our derivative of x and we get 4t minus 4, and now we know what that value is, so equals 20. And this actually allows us to solve for t, for time. So we get 4t equals 24, therefore t is equal to 6. And because of that, because we figured out our t, we can figure out our y, and given x and y, we can figure out our r. We can figure out our dy dt, and essentially we can figure out everything except dr dt directly, which of course we need to figure out as our final answer. So let's just note, so dr dt is our final answer, the total change in the, or sorry, the change in the total distance with regards to time, where r is the total distance between the two boats. So if we were just solving for dr dt, we'd get, we can divide this 2 out first. Note that. And essentially we get dr dt equals x dx dt plus, this 4t minus 4 comes from our x equation right here. The x equation we created before. So when we take the derivative of this x equation with respect to t, I should write that actually. dx, sorry. dx dt equals 4t minus 4. So that's where our 4t minus 4 comes from. Just taking the derivative up here. So we find dr dt is x dx dt plus y dy dt all over r, right? Because now we're just dividing this r on the right side. And so let's solve now, given the t that we figured out. Let's solve for we need to solve for x, we need to solve for y, we need to solve for r, and we need to solve for dy dt. So let's solve for y first. So y equals negative 5, 6 squared plus 6 plus 5 is equal to, I think I have it here. Let's see, 36 times negative 5 plus 11. Oh yeah, so is equal to negative 169 our x is equal to 2, 6 squared minus 4, 6 minus 2 equals 72. I think 46. But I can check to make sure. Yeah, 46. And then our dy dt, which we get by taking the derivative of our y, is equal to negative 10, 6 plus 1, which is negative 59. And finally, our r is equal to square root, going back to the first equation we had for r, x squared plus y squared equals square root of 46 squared plus negative 169 squared. So finally, solving out all of these equations, sorry, plugging in all of these values we found, we get our final solution of dr dt equals 46, and dx dt we were already given, right, as 20. So 46, 20 plus negative 169, negative 59 over square root of 46 squared plus negative 169 squared. And you can plug this into your calculator, and your final result will be, I think, should be approximately 62.18. So the main idea here was we needed our distance equation again. We needed a way to relate our x and a y. And in this case, our x and our y were related by both being functions, this time not one of each other, but rather both being functions of t. So we were able to essentially turn the whole equation into an equation of t by doing implicit differentiation with respect to t. And we were able to find out actually what our specific t was that we were talking about in our scenario by solving this derivative of x that they gave us. So they gave us derivative of x with respect to t was 20. So that allowed us to see what specific time we were at, time t, which allowed us to solve for y, x, and dy dt, which allowed us to solve for this implicit differentiation question or equation right here. Now I know that it definitely like looks pretty complicated with all these fractions, all these and dx's, dt's. But the important part to note here is a lot of this is like just algebraic manipulation, basically. So it's just imagine kind of if you ever kind of are getting confused, just imagine like you can rename some of these like fractions to like constants, like say dx dt is c or dx dt is b, and then just move around those constants, or at least those variables rather. And maybe that makes it easier. Sometimes it makes it easier for me. But yeah, um, and I guess one last thing I just want to note is that like don't feel discouraged by looking at these problems. And if you can like solve these problems like on your first run, or even with just a little bit of help, you should feel really, really good about the test, because for a lot of these problems, like we tried to make them at least a little bit more on the difficult side. I don't think that you'll find problems as maybe as intense or as multi-step as this, especially if you have 8 problems on the test. Um, but the concepts are definitely the same. And the idea sort of is if you can grasp these concepts, then you should be very well prepared for the test. Um, and I guess just a final closing remark. Thank you all for staying. Just one last thing I'd like to say is the SSC is a great tool. I know we have a bunch of different services. I can personally talk about peer tutoring, being a peer tutor. So uh, I mean, we're open every day except Sunday. So feel free to drop in sometime if you need any extra help, if you want to get another concept maybe more in detail, and if you want, more individualized help. But yeah, that's it for me. Thank you all for coming out, and hope you all learned something.